Welcome back, everyone. In this video, we'll continue with our applications of vectors. In this video, we will specifically be looking at freefall and horizontal projectiles. Here is a horizontal projectile, something that is being launched horizontally off of a cliff or a table or out a window. And we'll look at this this little GIF and talk about it in more detail as we go throughout this slideshow. Okay, first of all, free fall, some reminders. This is for things that are being thrown straight up, straight down. Our acceleration due to gravity is always 9.8 meters per second squared downward. This is, of course, in the perfect physics world, in the absence of gravity. If I skip over to this video here, I'm going to post this video with this lesson. This is a video that Brian Cox does where he visits the world's biggest vacuum. It's 4.5 minutes long. It does a classic experiment where a bowling ball and a feather are dropped. It's worth a watch. It's worth a 4-minute watch of your time. So acceleration is always 9.8 meters per second squared. Time up is going to equal time down for a ball launched vertically, and that's when that's for a ball to return to the same height. If an object is dropped, we'll just be mindful of that wording that if an object is dropped, then our VI, or our initial velocity, is 0. And then if an object is thrown up, an object is at the top of its trajectory, its velocity is 0. And I'm going to add a little subscript here because this little subscript is what we're going to add when we start talking about projectiles. That is velocity in the y direction is 0. So in the up and down direction, when an object gets to the top of its trajectory, its y velocity is 0. Okay, so here is an example, and this would be an example that I put up. I will talk through solutions on the next slides, but just to give you an example, these are questions that we've seen before. So if we've got an amusement park ride that is free falling for 1.5 seconds, and we're asked to find what is the velocity and how far does it fall. So for these questions, we are going to apply our VIF-DAT. So our VIF-DAT for this question looks like so. And then for part A, we want to know what is its final velocity after 1.5 seconds. So we need to go and find the kinematics equation that works for that. Okay, and then the second question, we're looking for how far has this ride fallen. The initial velocity in the y direction is 0. So we just plug and chug some numbers there and get that it's fallen 11 meters in that 1.5 seconds. Okay, so here's another example. So a tennis ball is thrown straight up with an initial velocity of 22.5 meters per second. It's caught at the same distance above ground from which it is thrown. How high does the ball rise? How long does it remain in the air? Okay, so here is part A solution to that, where we know that our final velocity at the top of the flight is going to be 0. Our initial velocity is 22.5 upwards. Okay, our acceleration, when we put that into our formula, it has to be a negative number because it is acting in the downward direction. Okay, and then we plug and chug and we find, hey, this ball is going to reach a maximum of 25.8 meters. Okay, the next part, if we're looking for the time that the ball is in the air, I'm going to take the starting and final, initial and final position to be the same at the same height. So our displacement is going to be 0. The initial velocity is 22.5 up. We have acceleration acting downwards, and then we end up with a math equation that we can factor and solve. The amount of time it will take for the ball to get to the height from which it is released, it will actually happen twice, right? Ball will go up and it will come back down, and those two times are either going to be at 0 seconds or at 4.6 seconds. Now, another way that we could solve this is to just find the time for 1/2 of the throw and multiply it by 2. So we could look for the time from the bottom to the top, find that time for half of the trajectory, and then multiply by 2. Okay. Okay, onward to projectiles. Now we'll talk about projectiles. We're going to talk about two types, horizontal projectiles. Those are things that roll off a table, and then other projectiles that are launched at an angle. So I'm just going to skip over to a fun applet on PhET. If you just Google PhET projectile motion, you'll end up looking at this thing, and you can take this cannonball and we can fire a cannonball and be like, oh no, I missed the target. Well, what do I need to change? Well, if I'm going to keep my shooting angle at 0 degrees, I'm going to need to change how hard I shoot that thing, or my initial speed. So I'm going to try backing it up a little bit, and I'm going to try firing again. Boom. Yay, 2 stars. Okay, and both of these lines show the trajectory that each ball flew in. These dots that are along the way are a way that we are going to use, or a way that we are going to analyze the motion of projectiles. So we'll see this in the ensuing slides coming up, and I'll explain a little more about it. But really, they're like ticker timers for velocity in both the x and the y direction. Okay. So the one that we're going to focus on, I'm going to hide the bottom noise. So the one that we will focus on is a ball being launched horizontally. What I'd like you to do, first of all, these arrows on this ball that's falling, these arrows are representing both the x and the y components of the velocity. So you'll see, hey, in the y direction, we know this, things are going to accelerate downwards. So as this ball gets further into its motion, it is accelerating downwards. Gravity is pulling it towards the ground. And the key thing to notice here is that that velocity vector, I'm trying to follow it with my mouse for you, that velocity vector in the x direction is constant. It does not change. Okay, and that'll have significant impact for analysis of questions going forward. Okay, so just some key terms. I'll go through these pretty quick. But initial velocity, that's just the velocity that a projectile is initially fired at. So we are going to, a key part of the vector analysis of projectiles is going to be breaking the initial velocity into its x and y components. Okay, our range, when we're talking about range, that just means the horizontal displacement, or d with the subscript x, and I'll explain that more in the next couple of slides. Okay, and then the amount of time a projectile is in flight just after it's released, just before it hits the ground. So we're still analyzing two snapshots of an object's motion. Okay, and a trajectory is just the path that a projectile follows. Okay, in the perfect physics world, here are a bunch of trajectories. We just know conceptually, if we're looking at launching or throwing a ball straight upwards at an 80-degree angle, that ball is going to reach the highest it can. Its trajectory is going to reach a max height if it's being thrown at a steeper angle. So then as our angle lessens, like the next one is 60, and we see this green line, well, we're not going to go as high. If we keep going down to all the way to 30, you'll see that the horizontal range, we call this the range, how far, let's say we're going to the green and blue lines, how far something gets thrown, we call that d, or displacement in the x direction, is the horizontal range. You'll see the horizontal range is the same for both 60 and 30 degrees. And that's true. It's just another couple things change, like the amount of time of flight. But our horizontal range actually matches up for different pairs of angles. Okay, so 45 degrees, if you throw a ball at 45 degrees, that is going to give you your max range. Okay. Okay, so let's get to some key points here. So here's a ball that is going to be thrown horizontally off a table. We're just going to take some snapshots of this thing's motion. Now, I didn't create this PowerPoint. I pilfered it off the internet. So here's a good look at breaking this motion up into its ticker timer. Have a ball, launches, hits the ground with a bang, and then we can start to break apart this motion into its x and y parts. So this thing is just, what we're doing is just taking, it's ticker timer. It's just really ticker timer. And these blue dots that are along the vertical and horizontal lines there are just showing us a breakdown of where this ball is at specific moments in time. So in the y direction, we see our distance or our displacement between successive dots is getting bigger. So that means that we have acceleration And we know that acceleration downwards is 9.8 meters per second squared on the surface of the Earth. You'll notice that the amount of space in between each of the dots in the x direction, that amount of space is the same. So that means that our velocity in the x direction is going to be constant, or acceleration in the x direction will be 0. Okay, and I'll show you how we'll apply that going forward. Okay, so some key points. So just to formalize those couple of things, motion is accelerated in the y direction. And that's happening, of course, by gravity. Okay, velocity in the x direction is constant. Okay, our horizontal and vertical motions are independent. So we are going to separate these questions into both the x and y components. And we're really going to be doing VIFDAT, which we've done a bunch of. We'll be doing VIFDAT times 2. Okay, so here is what that looks like. Okay, so this is just another slide that shows gravity free path and the vertical free fall. So constant velocity versus accelerated motion. Okay, this is a closer in snapshot, and this picture will come forward because here is a look at what the two independent, this is the velocity in the horizontal or x direction, velocity in the vertical or y direction. So the velocity of this object is going to have, it'll have a vector that looks something like so, right? At that specific point in time, and that's just your Vx plus your Vy. So in this, I'm showing you this because we're often asked to find the speed or velocity. If we are asked to include direction, we're asked to find the speed or the velocity of an object at a certain point. And in the next question, I'll show you what an example of what that'll look like. Okay, so frustrated with taking biology, a student throws their textbook horizontally out a window 8.4 meters high with a velocity of 4.2 meters per second. How long does it take for the book to hit the ground? How far from the building does it land? And with what speed does the book hit the ground? Okay, so for projectile questions, we are going to apply our VIFDAT in both the x and the y directions. Okay, so before I even take information from this question, there is some information I can write on here that is going to be the same always. So those things are acceleration in the x direction is always going to be 0. Acceleration in the y direction is always going to be 9.8 meters per second squared. Okay, so in the x direction, I'm just going to put arrows here just showing that, hey, in the x direction, these two numbers are always going to be identical. Vi and Vf in the x direction are always going to be identical because velocity is constant in the x direction. Okay. Now, if we go and look to the question, we can also look at some other or put in another piece of information, and that is student throws their textbook horizontally out a window 8.4 meters high. So if we have an object being chucked and it lands over here, and this is 8.4 meters high, the displacement in the y direction, we know what that is going to be. Our displacement in the y direction, if this is our start and this is our end, our displacement in the y direction is going to be downwards, 8.4 meters. So in the y direction, it'll be negative 8.4 meters. I'm going to leave units out of the VIFDAT data just to keep it clear, but we know that velocity is meters per second, displacement meters, acceleration meters per second squared, time is always going to be in seconds. Okay. The other thing that we know is that time is always going to be the same, right? Time is time. It's a scalar. It's going to be the same in both the x and the y direction. Okay, so let's go and apply some math. So the first thing that we're going to do is find what the time is going to be for this thing. So I'm going to use information in the y column, and I'm going to use displacement is initial velocity times time plus 1/2 a/t squared. And in this line, I'm going to apply these little subscripts. That just means that that's happening in the y direction. And again, any numbers that we use that are vectors always have to be in the same direction, okay? We know also, I forgot to include this, our initial velocity in the y direction will be 0. That's for a horizontal projectile. If we look at our vector in our diagram, our initial velocity is pointing straight to the side, so there's no component of that velocity acting up or down. So our initial velocity in the y direction is 0. Okay, we don't know what final velocity is. We don't know what displacement is. We don't know what time is. Okay, so we have to go and solve some of these things. Okay, to find the time, we're just going to plug and chug some information from our from the y direction, or from the this y column, where our displacement in the y direction is negative 8.4. Initial velocity times time. Well, initial velocity is 0, so that term goes away, and then we're left with 1/2 times a in the y direction times t squared. Okay, and we can solve for t. T squared is going to be 1.714, where time is going to be 1.309 seconds. Okay, so I'm going to go and populate 1.3 seconds. Whoops. 1.3 seconds into our VIF table. Okay. Okay, so next, I just copy down the information that we just found. We just found that we know what time is. Okay, so next thing I'm going to do is I'm going to go for part B. For part B, I need to find out how far from the building does the book land, so displacement in the x direction. It's asking us for displacement in the x direction, or this value here. Okay, velocity is constant, and it's always going to be 4.2 meters per second. We just found our time to be 1.3 seconds, so the displacement that this book, or the amount of displacement in the x direction from the building is going to be 5.5 meters. Okay. So next, now if we want to find the speed that the book hits the ground with, to find the speed that the book hits the ground with, we are going to need to know this final velocity in the y direction. So this goes back to that that initial diagram where I talked about, hey, velocity at any single point, an object is, let's say we have this object, it's getting thrown off a building. Okay, it's going to have a trajectory. Just before it hits the ground, it will have a final velocity that looks something like so. That velocity will have an x component. Our velocity in the x component is 4.2. Whoops, 4.2. We're going to need to know this velocity in the y component. If we know that velocity in the y component, we can go and apply Pythagorean theorem and find out what our total speed of this object is just before it hits the ground. Okay, so we'll look at finding that. Final velocity is going to be equal to initial velocity plus acceleration times time. This is going to be in the y direction. Okay, this just allows me, just so I can leave out all of these subscripts for y. Okay, I'm just going to put over at the side, hey, I'm doing this in the y direction, just so I can keep it straight for myself. Okay, so velocity in the y direction. Our initial velocity in the y is 0 plus negative 9.8 times 1.3. We find that our final velocity is 12.8 meters per second in the y direction. Y direction. Okay, to find the total speed of this thing, or in this case, I'm just going to find the magnitude of this velocity vector is going to be 12.8 squared plus 4.2 squared. Okay, and then I can plug and chug and do some math on that and find that my final velocity is going to be 13.5 meters per second. Now, actually, I'm just going to list this as my, that's my speed, because I'm not going to include a direction with that. We could find that. We could find the angle that object hits the ground, but I'm just asked to find the speed, so I'm really just asked to find the size or the magnitude of that final velocity vector. Okay, so I'll give you a sec just to jot anything down that you need to. Okay, so our next example, we have a stunt car that drives horizontally off a 44.1 meter cliff and clears 54 meters of burning inferno. We want to find the speed needed by the driver to clear the burning wreckage below. So we want to find this initial velocity, and that's going to be in the x direction. Okay, so our VIF-DAT table, acceleration in the x is 0, acceleration in the y is negative 9.8. We know that the horizontal range is 54 meters. We know that the vertical drop is going to be 44.1 meters. So we'll make sure to include a negative there. Okay. Do we know anything else? Nope, I think that's it for now. Okay, so, except that our initial velocity is 0 because we were driving horizontally. So find the speed needed is what we're looking for. So what we'll start with is to find the time. We're going to find the time in the y direction. So if we look in the y direction and apply d is equal to vi t plus 1 half a t squared, our velocity in the y direction initially is 0. Our displacement in the y is negative 44.1. So that's equal to 0 plus 1 half times negative 9.8 t squared. We'll find that our t squared conveniently is equal to 9, and that our time in the air is going to be equal to 3. Okay, so if we know that that thing is going to fly for 3 seconds, which is totally determined by the how high above the ground we are. So we apply, so we look or analyze our motion in the y direction. We find that that thing is going to be in the air for 3 seconds. Okay, so the speed that's needed. So if we want to find the speed needed, we're going to look at displacement divided by time. Okay, and that's going to be displacement in the x direction, which is going to be 54 meters. The amount of time will be 3 seconds, and we find that our velocity in the x direction is 18 meters per second. And if we wanted to take that one step further, we could multiply by 3.6 and find that our x component, or our speed that's needed to clear that burning inferno of wreckage, would be 65 kilometers per hour. Okay. Okay, one more for you to try. So this is a skier that's launching horizontally off a cliff with a speed of 7.5 meters per second and lands 15 meters horizontally from where she took off. How high is the cliff? Okay, so we're looking for this displacement in the y direction. So like before, like the other questions, set up your VIF-DAT table, which it should start something like that, right? It should start something like that. And then from there, can you work to find the displacement in the y direction, or how high that cliff is for the skier to make that jump? Okay, and here's what I would do for my solution. I'd look in the x direction. I'd look at my displacement is equal to velocity times time. So my displacement in the x is going to be 15. Velocity in the x direction is 7.5. So our time, if we plug and chug for that, our time is going to be 2 seconds. Okay, then if we apply that in the y direction, we can say or find how high that cliff is by applying our other kinematics formula. So our displacement is what we are looking for in the y direction. Our initial velocity is 0. Okay, so that leaves us with 1/2 times negative 9.8 times our time squared. We can find that our displacement in the y direction is going to be 20 meters. Okay. Okay, can you please go and give practice problems from chapter 4, worksheet number 2 a try? There are 8 questions, 4 from Freefall and 4 from horizontal projectiles. Please give those a try, and I'll see you again next time.